Dear ladies and gentlemen, we're from Gain University and IMEC. Today I'm gonna share one of our research. The topic is multi-view target transformation for pedestrian detection. Despite the latest object detection method can achieve accurate localization and robust performance in various scenarios, occlusion is still one of the challenging problems. When occlusion occurs in a single view system, objects blocked by the others cannot be fully recognized. So one of the mainstream solutions for handling occlusion is introducing multiple perspectives to discover the occluded target. Compared to the single view setup, the multi-view system utilizes the information from different perspectives to discover the objects and improve the robustness to occlusions. In previous methods, they usually project the different perspective images to the ground plane, which is the BEV, bird's eye view, and overlap the projected features. So after the projection and overlapping, different view angle or different perspectives could be transformed to the same base. A certain pixel of the projected features are all point to the same location in the real world. So once we overlap them, we can easily aggregate the different view angles and use the convolution neural network to discover across the many single view features to see if there is a target on the ground plane. But this kind of strategy has a critical drawback is that perspective transformation will cause the distortion problem. The spatial structure of the pedestrian will break after the transformation. The features could be compressed or stretched over a large area depends on different locations. So it is hard for traditional convolutional neural network to explore the whole target because the kernel size is fixed, but the projected features are variant on different locations. So, so in our work, the proposed idea is that if we can somehow limit the distortion area, then the previous method can use the extracted features in a more efficient way. But how to limit the distortion area? The distortion would be various depends on the camera position or object size. But if we want to make the distortion area smaller, maybe we can compress the object before the distortion happens. To be more specific, in our proposed method, the first step is to perform the single view detection on each of the single view image. Just like the normal 2D object detection, we detect the pedestrian's bounding box on each single view image. So in the first step, the single view images are independent. They do not interact each other. We just use the 2D images to detect the pedestrians. When we have done the single view detection, we get bounding box of each pedestrian in a single view. For now, the features are not distorted yet. We can use the bounding box to extract the pedestrian features and compress it into a smaller size and lower dimension. And then we use these compressed features to build an auxiliary feature mask to assist the ground plane detection. For example, this rectangle is the original image features with predicted bounding box. We extract the bounding box feature and compress it into a lower dimension feature with only 1 by 1 channel size. And then we create a zero tensor with the same size of the image feature and insert the compressed feature into the corresponding position of the pedestrians, which is the foot point. To build an auxiliary feature map, we call it the meta feature. And finally, we concatenate the image feature and meta feature together. Like this, the shape becomes as height, width, and 2 time channel for a single view. We apply this to every different single view images and then perform the perspective transformation. So after the perspective transformation, the projected features will not only contain the original features, but also contain the projected meta features. Then we perform the ground plane detection on the overlap feature maps to find the targets. The reason why we create the meta feature is because if we can limit the object's feature size before the distortion happens, we could limit the distortion area. And this meta feature can give a hint to the model when performing ground plane detection. It will clearly indicate the location of the pedestrians that is detected during the single view detection. Here is the whole procedure. First, we feed n images with different view angles into the feature extractor and perform the 2D object detection to find the pedestrians of each single view image. And then we use the predictive bounding box to compress each pedestrian feature to build an auxiliary feature map and concatenate with the original feature maps. And finally, we project the features to the ground plane and overlap them to perform the detection and get the predicted occupancy map. This procedure can be easily added into many state-of-the-art methods if the method contains the single view detection and perspective transformation. They can easily plug our proposed module into their method to boost the performance. Here are some visual examples. We can see that the perspective transformation causes the severe distortion problem, which break the spatial structure. But the distortion area of our proposed meta features are limited. We can clearly indicate the location of the pedestrians for the detection model during the ground plane detection. In the experiment part, we follow the previous method to use MODA and MODP to measure the performance. We apply our module on 3 different state-of-the-art methods to compare the performance. In the well-tracked dataset, we can see that our proposed module can achieve better performance in most cases. And in another dataset, ModelView X, our method still can improve the baseline methods. We also conduct some evaluation study to verify the effectiveness of our method. First one is about the effect of the compressed feature size. We enlarge the compressed feature size to see the effect. We can see that smaller feature size can achieve better performance. That is because when we enlarge the compressed feature size, the distortion area will be enlarged too. Once the distortion area is enlarged, there will be ambiguity between each independent samples. We can see that with the smallest feature size, each of the pedestrian features will not overlap together. But with larger feature size, the distorted features will overlap together and cause ambiguity when perform detection. And the second experiment is about how to combine the image features with our proposed auxiliary feature maps. We can see that without the original image features, there is a large performance reduction. That is because our proposed meta features is only based on the single view detection. Once the single view detection fails to find the target, its feature will be dropped out. So we don't have any chance to find it again during the ground plane detection. That is also the reason why we call this map as auxiliary feature map. Actually, it just summarizes the single view detection results into a more effective format to assist the detection model to make prediction across multiple perspectives. Here is the comparison of the predicted occupancy map. Left column is the baseline method, and the middle one is our method, and the right column is the ground truth. Our method can draw a more clear map compared to the baseline. In conclusion, we propose a new transformation method to solve the distortion problem and make it easier to fully use the pedestrian features. Second, our method is not a whole new architecture. It is applicable to most existing multi-view detection methods to improve the spatial aggregation performance. And finally, in our experiments, the results show that our method can achieve better performance on 2 public datasets.